Contact and human dynamics from monocular video. Given a monocular video of a single person performing a dynamic activity, our goal is to estimate a physically plausible 3D motion. Existing methods produce accurate 3D shape and pose that result in small local joint errors. These motions look reasonable from the input camera viewpoint. However, the side view reveals visually and physically implausible artifacts. For example, noisy jitters and unnatural leaning. We also observe feet floating above or penetrating the floor, and moving when they should be in static contact. These artifacts appear highly implausible since they oppose our natural physical reasoning about human motion. For example, feet should be static and grounded when they're in contact, and motion is generally smooth and follows the laws of physics. This has negative implications for many downstream applications. In character animation, humans are perceptually sensitive to physical inaccuracies, and for tasks like scene understanding and action recognition, artifacts may drastically change the semantics of what's occurring in a video. In this work, we look to improve an initial 3D motion estimate using physics-based trajectory optimization. Optimization constraints are a natural way to express physical reasoning. However, jointly optimizing discrete foot contacts with continuous full-body dynamics is challenging and prone to local minima. To manage these challenges, we introduce a new strategy to extract physically valid full-body motion. We use a learned model to detect foot contacts from video that uses automatically labeled synthetic data for training. These contacts initialize a trajectory optimization which uses a reduced dimensional body model and simplified dynamics to handle complex motion. To evaluate our approach, we propose using numerous kinematics and dynamics metrics that capture the plausibility of a motion better than traditional pose benchmarks. We focus on videos of single people performing dynamic walking, dancing, or sporting motions. To make the problem manageable, we assume there is no camera motion and the full body of the person is visible. As input, our method takes initial 2D and 3D pose estimates from existing methods. In the first stage, a neural network detects foot contacts based on the 2D lower body joints. We train this network on a new synthetic dataset that includes RGB videos, 2D and 3D pose, and foot contacts that are automatically labeled with 3D heuristics. The dataset contains 65 motions retargeted to 13 different animated characters and represents a variety of actions. Open pose is applied to each video to obtain the 2D pose inputs for the neural network. The neural network is a simple, multi-layer perceptron that operates on a temporal window of 2D lower body joints. It outputs a binary contact classification for the toe and heel joint of each foot over the window. Using 2D joints as input features allows sufficient performance on real videos after training entirely on synthetic data. Next, we use the inferred foot contacts in a two-part optimization to refine the initial 3D pose estimate from monocular total capture, or MTC. The kinematic optimization estimates the inputs for the following physics-based step. This includes the ground plane, along with a refined full-body motion that respects the predicted foot contacts. Finally, the physics-based optimization finds a dynamically valid motion based on the initial kinematic poses and foot contacts. This reduced dimensional optimization treats the person as a rigid body with inertia that varies over time. It solves for the center of mass position and rotation of the rigid body, along with feet positions, contact forces, and contact timings. After optimization, an inverse kinematic step transfers motion back to the full body representation. The objective of this optimization is to closely match the input motion and foot contact times. Physical reasoning is applied through constraints. For example, motion must follow rigid body mechanics, feet are static and on the floor when in contact, and contact forces push away from the ground with reasonable magnitude. Overall, this results in a new, physically plausible full-body motion. Please see the paper for more details. We first show results from the contact estimation neural network. Our model makes smooth and accurate contact predictions after training on synthetic data. Quantitatively, our neural network outperforms multiple baselines on both the synthetic test set and on a small set of manually labeled real-world videos. Classifying contacts based on foot joint velocities of 2D or 3D pose estimations gives decent accuracy. However, these heuristics often fail when data is noisy or joints are static but off the ground. This is apparent in the following example, which shows neural network predictions are more accurate and stable than the naive 2D velocity heuristic. Next, we show qualitative results of 3D character animation from video. The output of our method is shown on the right. We compare our final result to the input from monocular total capture, along with the motion after only kinematic optimization. Looking at the torso and center of mass trajectory, we see smooth and natural motion after adding physics. From the side view, optimization fixes feet penetration from the input. In this example, the kinematic optimization fixes feet floating artifacts. The physics optimization moves the feet to avoid unnatural leaning. We also evaluate on synthetic videos with ground truth alternate view. From the input view, our method fixes a number of foot artifacts. From the alternate view, we see further improvement in stable foot placement that closely matches ground truth. Our physics-based optimization solves for center of mass motion, along with foot positions and contact forces. Optimized center of mass and forces are shown here. Our method generalizes to characters of varying mass and distribution. The mass difference is reflected in the optimal contact forces shown here. Quantitative evaluation of high-quality motion estimation is challenging, since traditional joint position errors may be low even for implausible results. We propose to use a set of physical plausibility metrics which quantify the visual realism of a motion. Kinematics metrics capture common foot artifacts, while dynamics metrics measure the plausibility of contact forces. On the synthetic dataset, we compare the final result from physics-based optimization to the input from MTC and the result after kinematic initialization. The kinematics metrics measure how often foot floating, penetration, and skating appear. Lower is better for all three. As shown, these metrics are generally best after kinematic initialization and substantially improve upon the input motion. Dynamics metrics measure ground reaction forces defined as the total contact force on the person. Contact forces are an output of the physics-based optimization, but for the baselines, these are estimated based on center of mass acceleration. The mean and max GRFs of our method are reasonably close to the person's weight, whereas baselines give implausibly high values. During ballistic motion, we expect no contact forces. However, accelerations of the baseline motions incorrectly imply their existence. In summary, we have presented a method to estimate foot contacts from video, followed by physics-based optimization to reconstruct plausible human motion. We evaluated estimated motion with proposed metrics of physical plausibility, showing large improvements over the initialization. Though our results are promising, their quality is limited by the input motion, which may affect the floor fit and final output. Additionally, our method assumes a static camera with no occlusions, and the optimization can be relatively slow. Thank you for watching.